Hey everyone. So today we have the chance to have a seminar from Ramon. He's working on the formation and evolution of the planets in the solar system and beyond, the aftermath of their formation and their ability to host a biosphere. He got his PhD in the University of Turku, Finland in 2003 on the aspects of solar system and three-body dynamics. Then he did his postdocs in Toronto at York University, then Queen's University in Kingston, the University of Toronto, and the Observatory de la Côte d'Azur. He became visiting scientist at the Institute of Astronomy and Astrophysics in Taipei in 2011 and associate professor at the Earth Life Science Institute in Tokyo in 2014. He is now a permanent researcher at the Konkoly Observatory in Budapest since last year, as well as part-time professor at the University of Oslo. He was also my internship advisor a couple of years back and the person that inspired me to pursue research. So it feels really special to me to have the opportunity to introduce him today. Today, he's going to talk about the relation between giant impacts in the planetary system formation process and the habitability of the planets. The floor is yours, Raymond.
Thank you, Emily. So we all know who is responsible for inviting me here. Thank you very much for having me here. It's my first visit to the IAP. And so far, I've really enjoyed it, and I hope to be back in the future. So when I was requested to do a seminar here, I was like, well, gosh, what should I talk about? Because I mostly do solar system research. And then Emily said, oh, but we have a vibrant exoplanet group. So I said, okay, I'll do something about exoplanets. My primary research is not in exoplanets. I mostly do solar system stuff, but I do sometimes dabble in exoplanetary research because, you know, we're finding new planets and we don't really understand how they form. And one thing is because I was working at the Earth Life Science Institute in Tokyo for 6 years, which is a highly interdisciplinary institute where you have a camp of planetary scientists and a camp of biologists and chemists. And, you know, we're trying to bridge that gap between us and try to understand how you can get life on a planet like the Earth. So I come from a very interdisciplinary background. And during the course of that, we realized that if you want life on Earth, you need to have specific ingredients, specific conditions. And I wonder if we need the same on exoplanets. So that is what I'm going to talk about today. So an overview is I will first talk about some mechanisms and formation for the Earth itself. Then what is the environment on the early Earth and what do we need or we think we need in order to kickstart life? So I'm going to start from the solar system and then I'll work my way towards exoplanets, and I hope you understand why. Then there's something called late accretion, which changes the environment on the Earth. Then you have things like crust formation, which is an indicator when accretion has stopped and when the planet environment is basically quiet enough that you can start building life. And then I'm going to essentially take that package and place it onto exoplanets and see what the formation simulations and so forth can tell us. So if we want to form the Earth very briefly, okay, what happens is that the sun is surrounded by a disk, which more or less looks like a pizza, and it is composed of gas and dust. And from that dust, you start to form small bodies, like meter size to 100-kilometer size, asteroids, comets, that sort of thing. And the idea is that those start to stick together when they meet. Sometimes they bounce, but frequently they start to stick together and then they grow larger. And you start to form small planets or planetary embryos, the size of the Moon, Mercury to Mars. They then become dynamically unstable. So their eccentricities grow. The eccentricity is a measure of how elongated the orbit is. They cross each other's orbits, so eventually they collide. And in that way, you can build larger planets like the Earth and Venus. And the Earth had a very giant impact, some 100 to 30, but most likely 60 million years after it started, which formed the moon. That's in an overview. So you have a stepwise growth of the mass of the planet like the Earth. And from, crystallization ages of small minerals called zircons in lunar samples that were brought back by the Apollos, you can essentially get a model age for when the moon formed, and the most likely age is about 4.51 billion years ago, which is roughly 60 million years after the sun formed. Okay, so the moon was formed within the first 60 million years of the history of the solar system, and the Earth a little earlier. So what I do is I run simulations of that. So here I'm going to give you an example. You have the semi-major axis is basically the size of the elliptical orbit, so how large the orbit is, around the sun. And then the eccentricity is a measure of how elongated the orbit is, with a circle having an eccentricity of 1, growing larger, and then a straight line has an eccentricity of 1. You're basically just falling straight onto the sun. Here, I place small particles, so, whatever size I want, there's a few thousand of them that are interacting, and I put Jupiter on its current orbit because Jupiter most likely grew before the Earth. We know this from other samples. And I plug this into the computer with only gravity, and I watch what happens. And it won't play, and I don't why does it not play on the Zoom? Yes, it should, but it's not doing it. Can I play it here?
You cannot.
No. But it always plays.
Yeah, can you try?
Yes, I'm trying it here, but it's not playing.
I'm not sure.
Well, this is very embarrassing because normally it always plays. So, shit.
Remove the full screen.
No, something has gone wrong. I want to see. You can see that I start to form small planets close to the star, and they're red, right? So the material I start with here is red, and I form small planets here, and that means that they grow from local material only. They basically absorb only the material in their vicinity. But now notice that when they grow larger, their color changes. They start to become more blue. So in other words, they are not only absorbing the material very close to the sun, but they are essentially absorbing material from all through the disk. Everything gets mixed. Okay, this is interesting because this explains why the Earth has water. If the Earth had formed only from material very close to the sun in this region, so this red region here, the Earth would be dry. We wouldn't have water, and it wouldn't be raining outside. Okay, so I'll run it one more time just to show you. So you see that the blue particles and the yellow and the red are first separated until about 4 to 5 million years. And now things are starting to get mixed because things are tossed back and forth. And the red planets that grow here, so you have inside-out growth, and here you grow, here you're too far, it's too slow. And then eventually they're going to become blue because they're also absorbing material from farther out. And like I said, that's where the volatiles and the water and so forth are coming from. In the 1950s, there were two scientists, Miller and Urey, who did an experiment. They started with a chamber that had water gas, methane, ammonia, and hydrogen. Just those. And they had a spark discharge. And then what they did is you have heated water and so forth, a gas inlet, You have the methane and ammonia coming here like that. You have heated water. It went in through here. You have a spark discharge. And then you have this mixture of gases. You send lightning through it because that's essentially what a spark discharge is. So you send lightning through it, you cool it, and then you end up with something here. And to their greatest surprise, the material that ended up here is like a tar, but it had organic compounds. So stuff that you find in the soil and in plants and everything like that. And they produced extremely complex organic compounds from these very simple molecules. And they were like, okay, how is this possible? What is happening here? And what is key is that these gases are reduced. Okay, so there's almost no oxygen in here. The carbon is bound to hydrogen. The nitrogen is bound to hydrogen. Only hydrogen has a little bit of oxygen in it in the form of water, but everything else has no oxygen. So it's very reduced. So the question that people in astrobiology are now asking themselves, if you can form organic compounds from this, could that be a pathway towards origin of life? And what kind of planet do you need in order to get an environment that looks like that? That's the main question. So I will introduce something called oxygen fugacity, which is a measure of how much oxygen you have to be able to bind to other molecules. The lowest number typically seen is at the iron boostite, where you have iron as metal reacting with oxygen and you form iron, usually 2+, so FeO, because the oxygen is always 2-. But if you have more oxygen in the system, you can basically start to oxidize silicates like this, and you have Fe3O4. O4 is 8- because the oxygen is always 2-, and Fe3 means the ion is 2.6666+, right? Because you need to divide 8 by 3, you get 2.66666. If I introduce even more oxygen into the system, I get Fe2O3. Here the ion is 3+, which is the most oxidized form of ion that we see. So depending on how much oxygen is available in the planet or in a mineral or in some environment, the ion will exist either as a metal, as 2+, as 2.6+, or as 3+. Basically depending on how much ion or how much oxygen we have in the system. And it turns out that in the Earth, in the mantle of the Earth, we are typically at this FMQ value, so it's 2.666+. But in Mars and the Moon, we're closer to IW, so it's ion 2+. So the idea is that the mantles of the Earth, of the Moon and Mars are more reduced, are lower oxidized than it is for the Earth. Now remember what I said, for Miller-Urey, you want a reduced environment. So that would suggest that the Moon and Mars would be better environments than the Earth for building origins of life. Is that crazy? Maybe. It sounds crazy that a small planet like Mars might actually be better for starting life than the Earth did. Okay? Let's keep that in mind. The next thing that you can do is you can take samples from the Earth or from Mars or from the Moon, and you can date them with radioactivity, uranium, lead, or other systems. And you can then measure the oxygen fugacity of those samples. So you get a relationship between the sample age, which is essentially a proxy for time for how the planet evolved in the interior, like volcanism on the Earth, and we have mantle turning and plate tectonics and so forth. All of this evolves with time. And oxygen fugacity of the mantle. The idea is it possible that interior processes within a planet can change the oxygen fugacity over time. Let's say you solidify something, the planet is cooling, maybe you change the mineral composition of the planet. It turns out that this is not the case. So even 4 billion years ago, or even older, terrestrial samples show an oxygen fugacity that with large scatter, okay, fine, with large scatter are around the FMQ value, while for Mars and for the moon, they are systemically lower. Even 4 billion years ago, so it hasn't changed. So in other words, when the planets formed, their mantle composition has stayed the same. You have interior processes like convection and so forth, but the composition doesn't change. Can anybody tell me, especially from your group, if I have a volcano on the Earth, what kind of gases come out of that? Do you know? You can say it in French. Oxygen? Pardon? Nitrogen, yes. Hydrogen, no. Next. Yes. Carbon dioxide? Yes. Water? Yes. Methane? No, not really. Ammonia? Not really. Now, what do the gases that I just listed have in common? They are oxidized. CO2, N2 is not oxidized, but that's essentially the nitrogen becomes a noble gas. And water is oxidized hydrogen. So on a planet like Earth, whose mantle is fairly oxidized, the gases that come out of the volcanoes are water and CO2 and some CO. On Mars, which is more reduced, you get less water, you get a bit more hydrogen, and you get something like methane. What does Miller-Urey want? Hydrogen, methane, ammonia, and some water. What does it not want? Carbon dioxide and water. So, in other words, Mars is much smaller than the Earth. Its mantle is more reduced. We know this from measurements of samples, but it outgasses reduced gases. Earth is much larger, so it can hang on to its atmosphere. Mars's atmosphere is escaping. It's too small. But the gases that come out of it are not suitable for origins of life. So we have a problem. How then, if Earth is not a good environment for building the planetary building blocks for origins of life, what can we then expect on other planets? Should we even be looking for life on Earth-like planets, or should we focus on smaller planets like Mars? We have a bit of an issue. The problem with Mars is that it's very small. Its atmosphere is almost gone. So on Earth, we have a pressure of about, 1,000 millibars or something like that, give or take if there's high pressure or low pressure. Here it's predominantly low pressure, right? Because it's one after the other. That's why you have such bad weather. On Mars, it is 6 millibars. So it's 0.6% of this pressure that we have on the Earth. And from xenon isotopes, xenon is a noble gas. Helium is the first one. Then you have neon, argon, krypton, and xenon is the most heavy noble gas. From xenon isotopes on Mars, from a particular meteorite, we know that Mars's atmosphere was mostly gone about 4.2 billion years ago. So just imagine that you have Mars forming, and it has all these reduced gases, so it seems like a good place to start to form life. But then, lo and behold, because it is so small, it can't hang on to its atmosphere, that atmosphere is gone 300 million years later. Life doesn't like that. So maybe there was some life on Mars that started to form, but then it stopped because the planet was not a good enough cradle to hang on to it. While for the Earth, we have the atmosphere, but we didn't have the right building blocks. So does Mars represent a dead end? Please excuse the pun. Maybe it does. So we need to think back about Earth. And xenon isotopes on the Earth tell a story that there must have been some hydrogen in the atmosphere of the Earth a very, very long time ago, about 4.5 billion years ago. This is great because hydrogen is one of the building blocks that we need for pre-RNA life. So the question is, where did hydrogen come from? Because I just told you that the gases coming out of the volcanoes should be predominantly oxidized, not reduced like hydrogen. And the answer is it probably came from the sky plus water. So if you want to change the environment on the Earth, which we need to if we want to get hydrogen in the atmosphere, we need to do something to the Earth. I'll show you in a tick. And one way to do that is to hit the Earth with material coming from the sky. So late accretion is a fact because we have craters on the moon. So when the moon formed, it was constantly pummeled and struck by small bodies, asteroids that are a few meters to 100 kilometers across, and they form craters on the moon. If you hit the moon, you also hit Mars, you also hit Mercury, you also hit the Earth and Venus and all the other planets because you can't only strike the moon. So the Earth must have been hit by planetesimals just like the moon. And the problem that we have is that the Earth was hit. The Earth accreted a little less than 1% of its mass after the moon formed, but the moon was a lot less. It is a factor of 1,000 greater, while the expectation is about 90. So in other words, if I'm shooting darts, I expect to hit the Earth 100 times more frequently than the moon. Because of gravitational focusing, the Earth is a larger target. But from samples from the Earth and the moon, we know that the ratio is 1,000. So what was happening that it was preferentially targeting the Earth? Right? That makes no sense because gravity shouldn't care. So how can we match all these constraints simultaneously? And we came up with an idea. In 2016, we said, suppose that you hit the Earth with one big object, about the size of the moon. Then you dump a lot of material onto the Earth and you ignore the moon, and then everybody is happy. So we ran some SPH simulations in 2017, and if you hit the Earth at an angle of about 30 degrees or 45 degrees, then the red material is essentially the metal component of the interior of this lunar-sized body. You can put that in the mantle of the Earth, and then you can explain why we have gold. So does anybody here have a gold or a gold watch or a golden ring? Anybody? So you shouldn't be able to, because when the Earth forms, gold is considered what is called highly siderophile. So it hates being in silicates. When the Earth forms, all the Earth should be in the core, in the very deepest part of the Earth. It shouldn't be in the crust. Yet we find it because, you have gold rings and there's gold in Fort Knox and everywhere else. There's probably gold in the French National Bank, but it shouldn't be there. It should be in the core. So why is it there? Because of this. This happened about, 4.5 billion years ago, and this is why we think there's gold in the Earth's crust. Are you going to move, buddy? Yes. If you add metal, such as iron, that comes from the interior of that body to water on the surface, you can get hydrogen. In fact, you don't need to add a lot. Even if you have a pre-impact carbon dioxide atmosphere of, let's say, 10 bars or 1 bar, You know, you can get a huge amount of hydrogen from a small body impacting even an asteroid of 200 kilometers, hitting the Earth. If it mixes with the water, you can get a lot of hydrogen. Hydrogen is a reducing agent. If you have any carbon dioxide, it will replace the oxygen and you get methane, you get ammonia, you get all that stuff that we need for prebiotic chemistry according to Miller-Urey. So that is why we think that this event changed the game. Through this impact that we had about 4.5 billion years ago, we changed the environment on the Earth. Temporarily, because this hydrogen atmosphere goes away, but we changed the environment. So we set it up for being able to produce all the molecules that we need for origins of life. It didn't last long, maybe 100 to 200 million years, but we were able to somehow do it. So the question is, can we do this on exoplanets? And like I said, this happened about 4.5 billion years ago. So we think because all the lead ages that we get for terrestrial samples, they terminate at about 4.48 billion years ago. We see it in xenon isotopes, we see it in lead isotopes, we see it in uranium, we see it in many other systems. So this was the last time that impact was so massive that it melted the mantle of the Earth. You reset the chronometer because lead, which is the decay product of uranium, is a volatile element. It has a melting temperature of about 500 degrees. So if you heat the mantle above 500 degrees, you melt the lead, you reset the ages. Cosmochemistry 101 for when you go to university. So the Earth's mantle has an age, and the atmosphere have an age of about 4.48 billion years. After that, it was nice and quiet. We see this also with crust formation. So lutetium and hafnium are two metals which trace crust formation. This is a forbidden zone that I have here. This is the bulk silicate Earth in terms of changes in hafnium isotopes. This lutetium-176 decays to hafnium-176. And all the data are here. And the intercept is roughly at about 4.5 billion years ago. So after that huge event, that huge impact, the Earth started forming a crust, and it has been forming crust for the last 4.5 billion years. Ergo, we haven't had a major event striking the Earth in the last 4.5 billion years. You can do the same thing on Mars. You can determine from Martian samples and from analyses, when did Mars first form a crust? And it turns out that it was extremely early in the history of the solar system. It was about 20 million years after the formation of the sun. So Mars formed in about 5 million years, and it had a crust by about 20 million years. Earth formed longer, but because of the moon forming event and the other thing, it didn't form a crust until about 60 million years later, right? Or 80 million years. So these are two maybe end member times that we can keep in mind if we want to start forming a crust on exoplanets and start to see if they could be habitable. In other words, should we expect similar timescales on exoplanetary systems? Does anybody not know this equation? Do you know about the Drake equation, any one of you? You know it? It's gorgeous, isn't it? Except that there are several quantities in here that we know almost nothing about. So the first one, this is the number of civilizations. This is what we want to compute, right? We have the average star formation rate, although in the past, about 7 billion years ago, there was a starburst activity in the Milky Way. So a lot of stars are about 7 billion years old, or they no longer exist. We have an idea now from all the exoplanetary stuff about the fraction of planets. But the average number of planets that can potentially support life, that is still kind of uncertain. We're getting there. I think in the next decades or 2 decades when I retire, we might actually have a good proxy for what this number could be. The fraction of planets that could support life, that develop life at some point. Now, that's an interesting one, because maybe Mars actually supported life in the beginning, but couldn't develop it later on because the planet essentially died off. And Earth should not have had life, but because we changed the environment, maybe it was able to get life, well, it did, and then carry on for the next 4.5 billion years. Okay? So this is a quantity that really requires planetary plus other sciences. The fraction of planets with life that actually go on to develop intelligent life. Are we actually intelligent? We tend to think so compared to other animals, but sometimes I ask myself if we really are that smart. So goodness knows if we can ever constrain this number. The fraction of civilizations that develop technology that releases detectable signs of their existence into space. Fermi's paradox, right? Where's everybody? And then the length of time which such civilizations release detectable signs into space, who knows? A couple of 100 years, a couple of 1,000 years, maybe not much longer than that. Don't think we will ever know that, but the other ones definitely. So there's hope yet that we can put some constraints on this number. The number of planets in the universe could be amazingly high. Right? So we have about 10 to the 11 galaxies, 100 billion, 100 billion galaxies in the universe. Maybe it's even more. Each one of these has 10 to the 11 to 10 to the 12 stars. Okay, but let's be conservative and say it's 100 billion times 100 billion. And each one of those stars has maybe 1 to 10 planets. So there could be 10 to the 22 to 20 to the 23 planets in the universe. That's insane. It's a number that you cannot comprehend, right? Even a billion. Let's say, I mean, India has a population of 1.5 billion people. If I were to shake each person's hand and it takes 1 second, it would take 48 years to do that. That's just 1 billion, right? This is orders of magnitude more. The numbers are so big that we can't really understand it, but that's the number of planets we could be dealing with. And none of them have some form of life? I don't believe it. And from the known exoplanets, most of them are in this region here, which we don't have in the solar system. We don't have a planet that is in between the Earth and Uranus and Neptune, but that's where most of them are found. Strange. Most of these are actually kind of gassy balls, so they're not very suitable for having life, but who knows? So now I'm getting to the heart of the matter. This was all a bit of an introduction, but it was also, what I want to provoke is thought and ideas and broaden people's horizons. So what I've done is I want to see, can I actually, if I want to form life on Earth-like planets, because of the likely mineral composition, the gases that come out of their volcanoes are oxidized, and therefore my postulation is that I need to have some sort of a large impact happening that can then temporarily change their environment, like happened on the Earth about 4.48 billion years ago, and then maybe some of them could develop something like life. So what I do is I run simulations wherein I try to form these kind of planetary systems around other stars, and I watch what kind of collisions I get and at what time. So here is such a simulation. It's very similar to the one that I ran in the beginning that I eventually got to work after some technical hitches, in which I have a star which is only 1/5 of the mass of the sun. So it's a small red star. And I place the particles this time between 0.2 and 2 astronomical units from the star instead of between 0.5 and 4. There is no giant planet here, and I kind of watch what happens. And now the color coding is the mass and not the water mass fraction. So I start to form planets close in, and then they migrate to the inner edge, and then they start to form, and they start to grow. And I have one here, and I start to form multiple ones of these planets, and it happens pretty quickly, because by 5 million years, I already have a suite of these kind of planets. Okay? So these simulations were only run for 20 million years. They take a very long time, because I have to, get very close to the stars, so I have to take many steps. But eventually you see that the number of particles is slowly decreasing, and I'm starting to form a cluster of planets somewhere here closer in. And I can then keep track of the kind of collisions that I get. And you get something that looks like this. So this is, as time goes on, the number of collisions with heavy bodies, so a body like the mass of the moon or larger, which is what I needed on the Earth to be able to create this nice hydrogen atmosphere. If I look in my simulations, the number of collisions with masses greater than about a lunar mass, it declines very quickly, and then I have this long tail. But it seems to start to die off between 25 to 40 million years. Some of these have run longer. I've also taken some data from simulations that a student of mine ran. Most of mine finished at 20. Some of them I've continued for a little bit longer, but by about 20 to 25, 30 million years, most of my collisions are finished. That's cool. Because I told you that Mars formed the crust about 20 million years after the sun. Is it possible that that is because Mars didn't suffer any more major collisions after about 20 million years? That the environment on Mars was quiet enough that it wasn't reset and it started forming a crust? If so, then the expectation is that it's the same for these planets. Is that a coincidence? I don't know. So what I think is that these exoplanets, the last time that they suffer a major impact is about 20 to 40 million years after they start forming. And then it's the same story as the Earth. Almost all of them suffer these kind of impacts, except that it happens earlier. But after that, maybe they have a temporary hydrogen atmosphere and they can start to develop origins of life. And a student of mine has just finished some simulations trying to form planets around different stars, and you get systems that look like this. So for very low mass stars, I don't get any significant planets. For a 0.2 solar mass, I get planets ranging all the way here, and the more massive the star, the more massive the planets that I'm getting. Now, these ones, we haven't tracked the collisions yet, but I just want to show you the kind of diversity of planetary systems that we can build in the computer. Right? So all of these are different. I start the simulation with almost the same initial conditions, and yet the outcome for all of them is different. That's the fun of doing these sort of things. Could some of these planets be habitable? I think so, but you need to have collisions. So this is my last slide. I'm at 45 minutes, so that's good. So some conclusions and open questions. So the first habitats for life on Earth could have been 50 to 100 million years after the solar system formed. And we have a paper about 4 years ago where we think that life started on Earth about 4.3, 4.4 billion years ago. Planets like Earth tend to have oxidized mantles, but smaller planets like Mars have reduced mantles, which is more conducive for origins of life. But the problem is that you have a small planet like Mars tends to lose its atmosphere. So it may start life, but it can't continue. Every planet that forms goes through a phase, what is called a magma ocean, in which essentially the whole planet is molten and it starts to solidify very slowly from the inside out. For the Earth, the last time that happened was about 4.48 billion years ago, but for Mars, it was 4.45, so almost 20 years after the formation of the sun. So Mars was nice and quiet 20 million years after, and maybe that is when it could have started to develop some form of primitive life, while Earth had to wait a little bit longer, and it needed to be induced with this large impact. And large impacts, I think, define rocky planet formation. This may not be entirely true, but I think that is where we're going. And they're mostly done by 30 million years. So are large impacts on Earth-like planets with oceans, that's key, they need to have water because otherwise you can't get the hydrogen. Are they needed to kickstart origins of life? Yes, I think so. I don't think I can ever really prove it, but given all the geochemical constraints and what we know from planet formation and what we know from pre-biotic chemistry, I think this is necessary. Now, I realize that this was a very highly interdisciplinary seminar, maybe not what most of you are used to, but what I hope is that something up here will be like, hey, this is interesting, this is cool. Maybe we can do some observations or find some experiments or some data that could support or deny this claim. Thank you very much.
Is there any questions?
Thanks, Ramon. Very nice talk. Of course, as you said, nobody here is specialized in chemistry or things like that. But I have a naive question. If I understood you correctly, you need to kickstart life, you need an ocean before, a planet with an ocean, and then a late veneer which comes and creates this reducing environment that you need.
Yes.
So far, so good.
Yeah.
But this very fact, this very event, the veneer, shouldn't it vaporize the ocean, which will be lost?
Well, but if you hit the Earth on this side, if you hit it where Paris is, right? Or let's say in the Atlantic, would you expect the Pacific to also boil away?
I have not the slightest idea.
Well, so this is the problem. So people like Norm Sleep and Kevin Zanla, they say, oh, you hit the Earth with a large impact, you boil the oceans. But I think that's ludicrous, because if I hit the Atlantic, I should not expect to boil the Pacific, because there's no energy input on the side of the Pacific. And you do not transfer that energy all across the globe. So one idea that I have, whenever I get time, because my to-do list is this long, unless somebody gives me like an ERC or something, that would be nice. Then I can hire postdocs and do it. But one thing is to basically run with, let's say, with ISAIL or run SPH impact experiments to actually verify if a large impact boils the oceans. I don't think it does. Just because you add enough kinetic energy that is equal to the latent heat of the oceans doesn't mean that they actually boil away, because then you need to hit it from all sides, and you don't do that.
But I guess it will depend on the total mass of the ocean, if it's a very deep or a less deep or whatever.
Well, but the primitive oceans were deeper because we know that the Earth has lost water over time. But again, if you hit it here, do you actually boil it also on that side? And I don't think you do.
Thanks.
But this Moneta event essentially was so large that, you also saw this rain. So you have some metal rain coming actually from the sky and going into the oceans, and that's how you get the hydrogen. But it melted the Earth. So that in that case, yes, you boil the oceans. Not directly, but because of all this other stuff that keeps raining down that is in some orbit around the Earth. But in one shot, no.
Thanks.
Other questions?
And they wanted me to talk about exoplanets, and this was the only thing on exoplanets that I have ready. So,
how many simulations did you run to get to those results?
56.
Thank you.
And these were run on GPUs, on graphics cards. So that's why it takes time, because you can't use that many at the same time.
Actually, I have a question. So, based on the instruments we have today, is there discovery that you would find very exciting that would help to in your work, you know, or something you are waiting for particularly? Like, I don't know, in the characterization of the atmospheres of exoplanets, are you expecting something to happen that would really help to understand?
Yeah, so that's a very good question. I haven't really thought about it that far ahead, but it's a very, very good question. One thing that I would look for is in young systems that are, let's say, up to 1 billion years old or 500 million years old, if there's any evidence for low mass planets with hydrogen atmospheres. So mini Neptunes or gas dwarfs, as I prefer to call them. I've seen that term floating around, but I really like it because really that's what they are. They're too massive, right? They are of the order of 5 to 10, 12 Earth masses. You want to look for planets whose mass is lower, but have a low density. So let's say you have an Earth mass planet, but with a density of 0.6 or 1.5 or something like that, instead of 5.5. That would be something that is very interesting because they could have a very puffed up hydrogen atmosphere. So that is the sort of thing that I would think about.
Thank you.
So low mass and low density.
Thank you for this super interesting talk, especially for someone who's definitely completely away from these topics. But there was just a logical issue I would like you to comment on. You mentioned Miller experiment, which says that when you have reduced element, then you can create these high and more sophisticated molecules.
Yeah.
And then you say, therefore, if you have an oxidized mantle, you can't. Which seems to me a little bit the other way around. I mean, you say that if it is reduced, then it works. And then you go to the opposite of it, which doesn't seem to work. So my question is simple, are there any experiments like the Miller one with oxidized molecules to begin with?
Yeah, so these kind of experiments have, okay, so maybe I wasn't clear. If in that case, I apologize. What I mean is that the Miller-Urey experiment happens in the atmosphere. It does not happen in the mantle. If the mantle is oxidized, you get oxidized gases. If you try to do Miller-Urey with, let's say, carbon dioxide and with water and with nitrogen oxide, it does not work because you do not form the species like that. Does that answer your question? Okay. Yeah.
I have another question, actually.
Please.
I'm a little bit puzzled by so the simulation you showed where you said that with very similar initial conditions or the same initial conditions, so you find many different architectures, right, and many different outputs. So I'm not, as you know, experts on this kind of simulations. So how do you interpret that, and how can we use the resulting statistics, you know, to think about exoplanet demographics from that, and how do you interpret like that? I mean, I know that it's so sensitive to initial condition that makes sense that the output can be very different on this the timescales, but how can we use this simulation to think differently, you know, the exoplanets demographics from the experiments we have today?
So the way I would think about that is essentially each one of these is a system. Mm-hmm. Every system is unique, both in the computer and that you observe. And the difficulty is that what are the input parameters that I need? And there are many: disk mass, accretion rate onto the star, initial solid to gas ratio, all of these sort of things, right? Can I basically put constraints on the input parameters that give me systems that statistically look like the observed ones? So if you want to do this, you need to run a lot of these. And are they statistically similar to what the statistical outcome is of the observed systems? And it turns out not always. So for example, the observed systems are more compact or are more spread out, or they're closer to the star than what you get in the computer. So then you know that something is missing in your model. Once you get there, yeah, then it's just a statistical game.
But how long would you need on a computer or supercomputer to run, I don't know, millions or thousands?
No. I would say, you know, you need about, if you go to 100 or 200, you really are at the limit. Okay. Because doing more just makes no sense. You only improve your statistics, but at some point, you also have to throw in the towel. I mean, these are run on GPUs, so I can run maybe 10 at a time on supercomputers, and they take 2 months each. So within a year, there's only so much you can do.
Okay, maybe 1 or 2 last questions.
I have a question. You mentioned the formation of organic molecules from a reduced atmosphere, but there is also a theory that organic molecules come from cometary materials or asteroids, and we know now that there are very complex even amino acids and sugars from asteroids. Yeah. What is your comment on that?
Yeah, so that is very interesting. So on carbonaceous chondrite meteorites, there are some that have these complex organic molecules. Could they have been delivered to the Earth? Absolutely. Could they have provided some building blocks for life? I certainly think so. But because they strike with such a high velocity, you have so much kinetic energy that you also melt them, or you change their composition. That is a problem that hasn't been solved. The other thing is you can't have a lot of stuff coming from comets, because the water on Earth isotopically is not the same as the comets in hydrogen isotope. So most of it must have come from carbonaceous and other meteorites. The water is chondritic on the Earth. Could you have delivered organics that way? Absolutely, but the mass is relatively low, and we have a lot of biomass. So this is a discussion that is ongoing, and I don't know where the answer is leading. But it's a good point.
Okay, if there is no question in remote, I suggest, do you have? No, okay. Yeah, that's me. Okay, so let's thanks again, Ramon. Thank you very much.
Thank you.